Hello everyone, I'm Xiao, a doctor student from Kyushu University. Thank you for giving me the chance to introduce our research here. The presentation today is about paper-based chemiresistive gas sensor using molecular imprinted soldiers for volatile organic acids detection. Paper, as flexible, porous, and eco-friendly substrate, can be used in the fabrication of simple, low-cost devices. For fabrication methods of paper-based sensors, printing technologies, including screening printing, low-to-low printing, live-value printing, and inkjet printing, can be commonly used in terms of the resolution and the printing speed. There are several merits of printing technologies, such as simple and rapid fabrication, free pattern design, and the precise deposition. So, paper-based gas sensors can be developed by printing technology with low cost, flexible, and high sensitivity. However, low selectivity is still the main challenge. Here, to let chemiresistive gas sensor be more selective, molecular imprinted soldiers are considered. In the preparation of MISG, templates, functional monomers, and crosslinker are dissolved in a solvent. And a highly cross-linked polymer that contains templates with covalent or non-covalent reactions to the functional monomer is formed. And nanoscaled imprinted cavities with recognition sites are then generated after removing templates by washing or heating. MISG can rebind templates with highly specific molecular recognition abilities. In this work, MISG was developed and used in fully inkjet printing process to prepare chemiresistive gas sensors. And the chemiresistive gas sensors were fabricated on photo paper with a 3-layer structure. A circuit layer by a commercial self-ink, a conductive layer by a carbon black ink, and a selective adsorption layer by different MISG inks. The gas response is induced by the resistance changes because of MISG swirling. Due to the selectivity of MISG, the target volatile organic acids would be selectively detected. The next part is the experiment part. The first is the carbon black ink formulation, as shown in the left image. Ketjen black as a unique carbon black with high conductivity was dispersed by naphthalene in IPA and the butanol, and then the rheology of the KB solution was addressed. The mixture was processed as in step 3 to obtain the final KB ink. Beneficial to the alcohol naphthalene dispersion system, the KB ink in low concentration was very stable. No obvious precipitate were found in settlement experiment after 120 days, as shown in the right figures. And next is for the formulation of MISG ink. The material in the table was mixed and processed as follows. And for the fabrication of MISG sensor, consumer inkjet printer is the fabrication device. 4 steps was included. For step 1, a series of self-IDEs was prepared by inkjet printing self-ink on the surface of photo paper. And for step 2, the KB ink was printed on the self-IDEs to form conductive layers. And for step 3, a selective adsorption layer of MISG was printed. Because the initial resistance and the gas response should be considered, the inkjet printing cycle of KB ink and MISG ink needs to be discussed. And finally, the printed MISG KB sensors were kept at 60 degrees for 2 hours to remove the templates. and realize the MISG layer curving. Next is the vapor generation and the gas sensing system, as shown in the figure. In addition, the vapor concentration was calculated by following equations according to the head spread method. The next is the results and the discuss. First is the characterization of ink formulation. As shown in the table, the key parameters of surface tension, viscosity, and the Z number were in appropriate range for stable inkjet printing. The follow distribution of 0.01% KB ink was shown in the lecture figure. And here, the D90 was used. The D90 means the follow distribution value in 90% in ink, and the D90 value of KB ink in initial state was about 160 nanometer and had a minor change to 108 nanometer after 120 days. This means that the formulated KB ink can avoid clogging of the nozzle and shows long-term stability. Because of the above properties of the formulated inks, efficient printing can be realized by consumer inkjet printers. In addition, the population threshold of KB ink with different concentrations was shown in the right figure. The concentration in red circle, which means the 0.055% KB ink, was chosen to fabricate KB layer with the appropriate resistance. Next is the optimization of MISG layer parameters. Based on 5 materials of MISG, the crosslinker monomerization and the template concentration was considered. Because of the gas response is induced by MISG swirling, the crosslinker monomerization had an influence on the crosslinking intensity of MISG, so the crosslinking content is very important. The peak response of 4.51% was obtained when the ratio was over 2. And next is the discuss of template concentration. The template concentration had a direct relationship with the formation of recognition sites. And the optimum template concentration was found to be 160 millimole in the right figure. And the next is about the real-time response of HA-MISG sensors to 3 volatile organic acids. Here, HA-MISG sensors imprinted by HA templates was prepared. 3 vapors, including HA, HPA, and OA, were chosen as detector vapors. To evaluate the selectivity of MISG, normalized response was calculated and showed in this figure. We can find that the response to HA vapor is larger than that of HA and OA. It indicated that a specific selectivity to HA gas was obtained. The next part is a summary of normalized response of different sensors to the 3 volatile organic acids. 5 sensors, including KB, MISG, and 3 different MISG sensors were prepared. The KB sensors showed poor response to target vapors, and the low response was observed for MISG sensors. And to obvious comparison, imprinting factor was used to evaluate the imprinting effect of different MISG layers. For MISG sensors, the highest response was generated in the corresponding imprinted templates. The imprinting factors of the 3 MISG sensors were shown as follows, which confirmed the effectiveness of this MISG in the paper-based chemiresistive sensors. Final is the conclusion. For the first point, MISGs were developed and used in fully inkjet printing process to prepare paper-based chemiresistive sensors for volatile organic acids detection. For second point, the rheological properties of the formulated KB ink and different MISG ink were evaluated for effective printing when using consumer inkjet printer. And for third point, high selectivity was confirmed by comparison the imprinting factors between non-printed sensors and the 3 MISG sensors. And for our future work, the paper-based MISG chemiresistive gas sensor provides the flexibility to develop a reliable device for human body odor, including volatile organic acids detection. That's all. It's my presentation. Thank you for your attention.